Good afternoon, everyone. In the last discussion hour, we have seen second order systems, how to model them as differential equations, and we saw how to solve for the solution or the response of the system, and we analyzed the response based on the roots of the characteristic equation of the differential equation, the poles and the zeros, and we found out whether the system response is oscillatory or non-oscillatory, and if it is non-oscillatory, whether it is critically damped or over damped. So at this stage we will now move on to designing practical control laws for manipulators. So what we will study now is linear control strategies. So this assumes that the model is represented by a linear differential equation, which might not be always the best representation of the system, but it's a convenience that we take in order to simplify the computational effort to design the control law. So in this figure, what you see is that the robot, which has the actuators, right, has the actuators. So we want those actuators to follow a certain trajectory, right? Moving the, let's say if we have the manipulator, we want to move it from point A to point B, and the joints will follow certain trajectories, right? Let's say if there is a joint here, and they are following certain trajectory, and as we have seen before, the trajectories can be defined in the task space, and those trajectory can be converted to joint space trajectories using inverse kinematics. So what you see here, this theta d dot, and theta double dot are the joint space trajectory. This is the joint space trajectory. So this block generates the trajectory of for moving the joints, and this is fed into the control system. Now the flow chart shown here, or the block diagram shown here, the control system generates the control input, and this is the output. That is when this control input tau is actually applied on the robot, then how much angle did the robot move, or how much velocity did the joints achieve, right? So this is the output, and you see here that this output is again being fed back into the control system, closing what we call as the loop, right? So this is the our closed loop control. This we have seen before also. So the other counterpart of this is open loop control. So in an ideal world, so when I say the ideal world, I mean that I model the system exactly, which is never possible in the real world. And so the model is accurate, or exactly the way the system behaves, and there are no noise disturbance, etc., which is also always the case in the real world. So if it would have been an ideal world, then the commanded torque can be directly calculated by the equation of motion. So tau is equal to m, this is the desired joint position, the desired joint acceleration. So by just putting in the desired quantities in the equation of motion, we would get a torque, and if we command that torque, and if it would have been an ideal world, then we would have, as an output, would have got these trajectories, right? But this never happens in practice because models are always inaccurate, and there is always noise and disturbance. In fact, there is a common saying in robotics is that all models are wrong and some are useful. So let me put that here. It's a saying that all models are wrong, which means that we can never exactly model reality, and some are useful. So we just want that much accuracy in our model that we are able to execute our desired task on the real system, right? So that much accuracy is required. And if you like go deeper into these aspects, you will find out that there's always a trade-off between model accuracy and the computational effort, because as you increase the accuracy of the model, the computational requirements increases also. So we have to find a trade-off, because we will like to run these control laws online in as fast as possible fashion. So computation need not be that heavy, right? So yeah, so the solution of this is, so this is the open loop control, which is not practical, and that's why we arrive at the closed loop control architecture, in which we also account for the actual state of the system and modify our control input by taking that into account. Okay, so we'll see closed loop control and use our example of second order systems to derive a few control laws and see how they perform. So the goal here is that, so what's the goal here? The goal is to drive the error to zero. I have mentioned this before also, but let me put this here again. So let me define error as the difference between the desired and the actual value. So this is for the state. Similarly, you can define for the derivative of the state. Right. So the goal is to drive it to zero, or if that's not possible, then keep it bounded. It should not increase with time, right? That then the system becomes unstable, and that defeats the purpose of the designing the controller. So the very first aim of the control engineer is to design a control law that drives the error to zero or keeps it bounded, and in some way or the other we are able to prove that this will happen. So some cases we are able to get mathematical proofs that the system is bound to be stable, and in some cases we get some simulation or experimental results also, right? So, and yes, even if there are disturbances, it should be able to achieve this. So this should be achieved even if there are disturbances. All right. Now, for an n joint manipulator, what we have seen earlier in dynamics, the system dynamics is highly nonlinear and coupled, right? The system dynamics is highly nonlinear and coupled. So the differential equation there is a coupled nonlinear differential equation, right? It's not as simple as our second order linear differential equation which we have seen in the previous discussion hours. And in order to simplify the design of the control law, we assume that we can achieve enough control authority by seeing each joint individually and controlling them individually. So we approximately use a strategy which is called as the independent independent joint control, right? So remember that this is an approximation, because in a manipulator no joint is isolated from the other joints, right? If you apply certain torque to a joint, it affects other joints also. But as a simplification, and for some cases, especially if the manipulator has actuators with high gear ratios, this approximation holds quite well. So it's a valid approximation and works in many cases. So what we will now think of is that n joint manipulator is equivalent to n single input single output systems, right? N single input single output systems, CISO. So this was one big multiple input multiple output system, a MIMO system. We can equivalently create a n single input single output systems. And then considering this, the individual joint can be modeled as second order differential equations, and from there on we can create control laws. So the focus from now on will be again back on the second order linear differential equation and how to control such a system. So closed loop control for second order linear differential equation. So let me pull up a picture here. So this is our system. Our system is a second order system, as I mentioned. So mx double dot plus bx dot plus kx, and there is a external force, the forcing or the control input F, right? So physically this would be equivalent to something like this, right? Mass M, there is a spring, there is the damper, and there is the external force F, right? And yeah, this is the x direction. So now F is the force applied by an actuator. Force applied by an actuator. So imagine that you, so the very first thing what we will see is trying to maintain a certain given position of the block, right? So let's say I want to keep the block in a position where it is slightly compressed, right? So you would have to apply certain force on it, and even if I want that, even if I slightly displace the block from its desired position, it should return back to it as fast as possible. So I like to, my aim is to design such a control law. So now this system, so this dotted line which divides this block diagram, so this is the, on the right is the physical system, and this is the controller which runs on a computer, right? So as I mentioned, F is the force applied by the actuator, and we assume that we have sensors for measuring x and x dot, right? Now this second order system that we have, so what's the goal? Let's state the goal. So the goal is to decide what should be F, right? The goal is to, the very first thing we should be clear is that decide F, because that is applied by the actuator. And that is how the actuator interacts with the system, right? So decide F such that the block maintains its position. Okay. So control law that we propose here, the proposed control law is F is equal to minus kpx minus kvx dot. So if you look closely, this will look very This resembles a proportional derivative control law, a PD control law, right? In which we multiply gains with the position and velocity of the system. Okay, so if we so the f will vary like this, right? So if we do like this, then our original system becomes mx double dot plus bx dot plus kx is equal to minus kpx minus kvx dot, right? So we replace f by this control law, because this is how we will vary the force depending on the x and x dot. So what this will do, this will try to keep the system at x is equal to 0 with x dot is equal to 0. So wherever we decide x is equal to 0, right, that could physically be a position where spring is compressed, elongated, but wherever we decide that would be x is equal to 0, that would be the desired position, and we'll try to maintain that position. So you see that if x is high, right, if x is high, it means you are displacing the block from its desired position, then there will be a force acting on it. And similarly, there is a part accounting for x dot also. So if you give some velocity of the to the system, there will be a force which will try to de-accelerate it and bring it back to rest. So bringing everything on the left hand side will give us this expression. And if we write this term as b dash and this as k dash, so this is our closed loop system. Because why closed loop system? Because you have already put in the control law in this. So this is the closed loop system dynamics. Now once you reach at this point, now you will analyze this closed loop system to comment on the stability of the control law. So now analyze this closed loop closed loop system dynamics for stability, right? And what parameters we have to choose here? So parameters to choose are kp and kv. Okay, so but the good thing is that we have already analyzed these kind of systems. This is the typical second order system, homogeneous second order differential equation, and we have analyzed this in depth in the last two discussion hours. So we can straight away write the condition in which this system will be critically damped. So for critical damping, and why do we choose critical damping? Because that gives the fastest non-oscillatory response for the system. So for critical damping, we know that this Xi should be equal to 1, which means that here b dash by 2 under root k dash m should be equal to 1, which implies that b dash should be equal to 2 under root mk dash, right? So by choosing our values of kp and kv, given the value of b and k originally, we can choose kp and kv such that this is satisfied. So now the values of kp and kv that will come out, those might be positive or negative, but the values of b dash and k dash, they should be always positive, because if b dash and k dash become negative, it can be very easily shown that the system will become unstable. So let's put this note down that kp and kv, the gains can be positive or negative, but the parameters of the closed loop system dynamics, that is b dash and k dash have to be positive, else the system will destabilize or will be unstable. And how will you show that? By finding the roots of the system and showing that the real part of the roots is positive, which makes puts a exponentially growing component in the response of the system, and thus the system will destabilize, right? So let's quickly do an example, a very simple one, just to clear out the understanding. So the same system, and let's take some values for the parameters. So m is 1, b is 1, k is 1, and the closed loop stiffness. So this k is the stiffness of the spring that is there in the system, and this k dash is the closed loop stiffness, and similarly b dash is the closed loop damping. So the closed loop stiffness is given to be 16. So we will have to find out kp and kv for critical damping, right? So we will directly use the above relation, that the closed loop stiffness and damping should satisfy the criteria for critical damping, right? So b dash is 2 times mass is 1 and k dash is 16, so this is 8. And b dash is b plus kv, so b is 1 plus kv is 8. Right, and similarly
सर आपका स्क्रीन नहीं विजिबल हो रहा है.
हाँ मैं शेयर कर रहा हूँ. Can you see the screen now?
Yes sir.
Okay. So k plus kp is k dash, which is 16, so Kp comes out to be 15. So very easily, by relating to the analysis of our second order differential equations, we can find out the gain values for a stable control law. Okay. Now the next technique that we will see is called as control law partitioning. So in control law partitioning, we we separate the control law into two parts. First is the model based part and the second is the servo part. So the model based part is uses the system information, which is the mass, the damping and the stiffness of the system, and the servo part is independent of the system parameters and just takes in the actual state and the derivatives of the system. So we have two parts here. The model based part and the servo part. Again, let me pull the image for this. So this is our system, and the system is again mx double dot plus bx dot plus kx, and this is the model based part and this is the servo part. So the aim, as I was mentioning, the model based part uses the system parameter knowledge to contribute to the control input, and here the system parameters are m, b and k, and the servo part is independent of that. It's in this case is a PD law on the actual state and derivative. So the same system which we saw just a while ago. So again, here we have to choose f, and we are free to choose the form of f, right? So the assumption is that we have enough control authority, or we have unrestricted choices about choosing f. So that gives us a license to a tailor-made f in such a way that the resulting system is greatly simplified. So the aim of designing this f, one aim is to choose the model based part such that the system reduces to a unit mass system. So the aim of model based part is to reduce the closed loop system dynamics to a unit mass system. So how will we do that is like this. So let us choose f, which is our original control input. Let us write that as alpha times f dash plus beta. So this is the original control input. Now in this modified expression, this is the new control input. And alpha and beta are constants here. Okay, so we have to again we replace f by this expression in the system dynamics. Now the goal is to make this system like this, right? X dot is equal to f dash. So now if you look closely, we can choose alpha and beta such that the terms on both sides, some terms cancel out and some factors, scalar factors are cancelled out, and the first equation is simplified to the second equation, which is the equation of a unit mass. So this is the unit mass equation of motion. This is also commonly called as a double integrator system. So if we choose alpha is equal to m and beta is equal to bx dot plus kx, then you will see that we get this simplification. So with those choices of alpha and beta, you can rewrite the right hand side as mf dash plus bx dot plus kx. So these two terms are cancelled out and m is cancelled out. So this becomes x dot is equal to f dash, which is the new input to the system. So now this is the, so after after this loop, closing this loop, so there are two loops here, you see the input to the, so this is the first loop, input to this loop is f dash, right, f dash. And the good thing is that now choosing f dash is very intuitive and very easy, because the system that we have to control now is just x dot is equal to f dash and not the full m x dot x double dot plus bx dot plus kx is equal to f. So by using the model based part of the control, we have reduced that system to just x double dot is equal to f dash. And for this system we choose f dash is equal to, as before, kv x dot minus kpx. Okay, now if we, this is the servo part, and as you see, there is no system parameters in this control law. There are just two gain values which will be chosen again by doing the stability analysis. So after this inclusion of this in the closed loop dynamics, the final closed loop dynamics becomes like this. And if I bring everything to each term to this side, this will be right. So this is the yeah. So this is the final closed loop system dynamics. So now in this case, choosing KV and KP has become even more easier, because directly for critical damping, the relation comes out to be KV is equal to 2 times under root KP, right? This is the beauty of this control law. And yeah, so basically, though the dependence on M, B, and K, the knowledge of M, B, and K is not required while choosing the gains KV and KP. It has become independent of M, B, and K, right? And this approach is similar to a broad class of approach known as feedback linearization, right? It is called as feedback linearization. So this is a form of feedback linearization, right? Here we need not specifically say this term, because our system was originally, also the system that we started with was originally a linear system itself, but the similar things happen there also, that we modify the control input by a change of variable, like we did here. We specified f as alpha f dash plus b, where f dash is the new control input, right? And by doing similar conversions, we bring it to a linear form like this, and then the second component of closed loop system becomes very straightforward to design. So this is the equation of motion of the so this is the closed loop dynamics of in the control law partitioning approach, and we can choose KV and KP given. So so ideally both of them are unknown, but we choose one of them, such as KP. KP is chosen by knowing what range of angular frequency we would need to work with. So you would remember that omega is under root k by m. So we choose some omega around which we would like our system to be, and we choose KP, and from KP we get KV, right? So this marks the end of the control partitioning approach. So till now what we have seen is that single input single output systems, and we have essentially designed position regulator systems that if we want that block to be at a certain position, x is equal to 0, let's say, and it is able to counter disturbances and and displacements away from its position, it comes back to its desired position, right? And if we extend this to, and we can very easily extend this approach itself for trajectory following. Trajectory following. So as I mentioned, in case of this, we have a trajectory which is known, let's say a priori. So by trajectory, we know the position. If we know the trajectory, that means that we know the position, the velocity, and the acceleration at each point of time, right? So, and we define the error, the tracking error, is xd minus x. So the desired minus the actual. Okay. Now the first part of this, so again we are doing the same control law partitioning, and we have arrived at this stage, x dot is equal to f dash. Now at this stage we choose f dash is equal to the desired acceleration plus kv times e dot. Note this, this is different from the above equation, kv times e dot and kp times e. Why e dot and e here? Because now we want to follow a certain trajectory, so it's not a fixed position which we can set, which we can always by change of coordinates set as x is equal to 0, right? It's not the case. So the desired value is changing every time, and we are trying to stay close to that desired value throughout the time. So here also basically this kv x dot can be thought of as x dot minus 0 and x minus 0, right? So similarly this is the case here. So we are minimizing the difference between the desired and the actual trajectory. Now this is the servo control law. Model based part is the same. We got the unit mass equation, and this f dash is the servo control law. Okay, now we put this f dash in the unit mass equation, so it becomes right. And if I take the x double dot term on the right hand side, so it will, this equation becomes, we can write the entire equation in terms of e and its derivatives. Now this is also a very useful form of system dynamics. This is the error dynamics of the system. What does this represent? This represents the error dynamics of the system, right? And the benefit here is that now again our goal is to drive e to 0, right? By driving e to 0, we are indirectly driving x towards x desired, right? So again we have a second order homogeneous differential equation which we have analyzed before, and we can straight away again write the relation that for critical damping we have kv is 2 times under root kp, right? And by choosing these parameters we can guarantee that e will go down to 0. Now if our model is quite accurate, uh, the system will start off itself at the with at the desired position and will continue to do so. But if let's say our modeling is inaccurate and the system does not, like, the e has some non-zero value at the beginning, but this control law will ensure that with time that e goes down to zero or a very less value, right? And by choosing kv and kp, we can basically tweak the how fast the error goes down to zero and what is the oscillatory uh, response of the system and all those things. So the insight here is that by doing control law partitioning, we transform the system to a unit mass system, and then choosing the servo control law becomes very straightforward. And finally we get a second order error dynamics of the system, and the gains can be chosen very intuitively. So a very common thing in designing control systems is the gain tuning, and if we bring the system dynamics to this form, then gain tuning becomes very intuitive, right? So this way you can track the trajectories on the manipulator. Now, important function of any control law is its ability to reject disturbances, right? So disturbance rejection. Now, in the same error dynamics equation that we wrote above, e dot double dot plus kv e dot plus kpe, we have now a disturbance, external disturbance. Now, in real life, this disturbance could be anything, but for analysis purposes, we again take some assumptions. So, for this, if this disturbance is bounded, right? Disturbance is bounded means that the maximum of this disturbance is always less than a certain constant, right? So let's say uh, if you plot the disturbance, it comes something like this. Like, it changes, it is not constant, right? But it stays within some values, which means that it's bounded. So if the disturbance is bounded, then it's a property of this differential equation, right? By the property of these differential equation, we achieve what we call as Bibo stability, bounded input, bounded output. So if the disturbance is bounded, it is guaranteed that the output is also bounded. It will the output will not blow up until the disturbance also blows up, and in that case we can't do anything, right? So we have to ensure that the disturbance stays bounded, right? And for analysis purpose, we will take an even simpler case when, let's have a look at a case when this f dist is constant, right? So, and we have, so in that case, let's see what's the steady state error. So steady state error means that, so whenever you see the term steady state written alongside any quantity, it means that that quantity is not changing with time, right? So the derivative of e is 0, right? So the above equation, what does it become? Only this term remains non-zero, and this is f test, right? So the steady state, let me write it as steady state. So the steady state error is this, and you see that higher the value of kp, lower the steady state error. Higher kp, lower ess. So that is one way to reduce the steady state error, but always using a very high gains is also not desirable, because that might uh, you know uh, drive your system in unpredictable ways. Very large control inputs can be applied on the system even for small disturbances, which is not always desirable. To entirely eliminate the steady state error, what we do, so to eliminate steady state error entirely, we modify the control law like this. And the additional term is, we have an integral term, right? So this is the d term, this is the p term, and this is the I term. So now this is the full PID control in action, right? So, and this is equal to x double dot, the unit mass system, and if we take this to this side, so the equivalent error dynamics is E double dot plus KVE dot plus KPE plus KI E dt, and this is equal to the disturbance. Now if we take derivative of this equation, so now this becomes a third order error dynamics. Right, third order error dynamics. But at steady state, all the derivatives will be zero, right? So this E triple dot, E double dot, E dot is equal to 0, and f test is also assuming constant, so it's 0. So what comes out is KIE is equal to 0, which implies that E is 0. So here we get that the steady state error is 0. So by adding an integral term, we can drive the steady state error to 0 by adding an integral term. We can drive E steady state to 0. But in practice, this KI term is generally chosen very small compared to the KP and KV term, in order to, because it results in a third order system, but we would like to keep this system as close as possible to the second order system, in order to not affect the other dynamics of the system, the stability and all, the poles and all. So KI term is generally chosen very less compared to KP and KV. So this is one way in which we can basically drive the steady state error to zero. So what we saw in this discussion hour is the different ways to design control laws, few different ways to design control laws. We started with the closed loop control approach, and the need for doing closed loop control is because the models are never accurate and there is always noise and disturbance in the real world. So just blindly applying a commanded torque based on a certain model of the system will never achieve the desired trajectories. So we need to take into account the actual state of the system also in order to modify our commanded torque and drive the error to zero. Now the goal is, as I mentioned, to drive the error to zero. And in independent joint control approach, we model the multiple input multiple output n joint system equivalently as n single input single output systems. Now for the second order linear differential equation system, a very simple control law is to choose f as the proportional and derivative uh, term, and that f acts as the position regulator control law, right? And we get the closed loop system dynamics like this, with a modified closed loop damping and closed loop stiffness, and the values of the gains can be chosen by going for the critical damping criteria, right? In the control law partitioning, we divide the uh, control design into two parts, the model based part and the servo part. So the model based part uses system parameters knowledge to reduce the system dynamics to a unit mass system or a double integrated system. And then for that unit mass system, we design the, and for that new input f dash, we take again a servo part which is the PD on the actual states, and there we get the final closed loop dynamics in which only the gains appear, and again the gains can be chosen based on critical damping. And this approach is similar. A similar approach for nonlinear systems is called as feedback linearization. And in the trajectory following, we just extend the above approach to trajectory case in which the error dynamics, the closed loop error dynamics can be derived, and again the critical damping gains for achieving critical damping can be selected. For disturbance rejection, we, for these differential equations, if the disturbance remains bounded, it's guaranteed that the output or the response will also remain bounded. And for driving the steady state error to zero, we can add a small integral term, a ki term, to drive the steady state error to zero, right? So yeah, that's it from my side for this discussion hour. In the next discussion hour, we will solve a few questions around this, and also discuss the subsequent topics that are there in the lecture slides. Okay.